This screen demo introduces an educational function of visual FEA, which illustrates the mathematical relationships between shear, bending moment and deflection diagrams of a structural beam. To start the program, select New Item from the File menu. Then, Project Setup dialog pops up for the setup of a new project. Click 2D Frame Radio button for a linear static analysis of a two-dimensional frame. Click OK button to complete the project setup. A 3-span beam is being modeled by clicking the nodal points using the grid system. The beam is composed of 3 frame members and 4 nodes. Turn off the grid, because it will not be used any longer. Select Element Property item from Assign menu, to define and assign the member properties. Element Property dialog pops up. You may identify the input items using the yellow tooltip with a short description about the item. Let's assume the beam has a uniform section and properties throughout the length. The default set of element property is to be used without any change. Thus, select all 3 members and assign the set. The state of assignment is confirmed by the color at the member, which is turned into red color. Choose Boundary Condition item from Assign menu, to set the boundary constraints. Boundary Condition dialog appears, and Node Selection button is automatically pressed. The dialog has the items of delta x, delta y, and theta, which specify the constraints of the displacements in x and y directions, and rotation, respectively. A fixed end condition is represented by the default setting with all 3 boxes checked. Unchecking the theta box makes a pin end condition. Double-click a node to assign this constraint. Click New button of the dialog to define the second set of boundary condition. Unchecking delta x box makes a roller support, constraining the displacement only in y direction. Assign this set of boundary condition to the remaining 3 nodes. The image of the beam model shows the state of the boundary constraints. Lastly, choose Load Condition item, to apply the external load to the structure. Load Condition dialog pops up. The first set is a uniformly distributed load, acting in y direction. Use the default value, 1, for its magnitude. Double-click the left member to apply the load. The direction of the force can be reversed, by clicking the +- button. Click New button to create the second set. The type and direction of the second set are identical to the first set. But, its force magnitude is -2. Apply the force to the right member by double-clicking it. Linearly distributed type defines a distributed force, with linear variation of force magnitude, throughout the length of the member. There are 2 values defining the magnitudes at the 2 ends. In this case, they are -2 and -1. Double-click the middle member to assign the load condition. Click Change Side button to exchange the end magnitudes. The size of arrows representing the distributed loads can be adjusted using the slider control. Define a new load set, as a point force applied in the middle of a member. The position of a point force is represented by the ratio to the length of the member. Set the magnitude of the force to 10. Double-click the middle member to assign the set. The scale of the point force image can be adjusted using the slider control again. Now, modeling of a 3-span beam is completed. From now on, the results of the beam analysis can be represented by diagrams, using the diagram menu items. Choose Shear Force item to display the shear force diagram. Use Adjust Diagram Scale item to change the scale of the diagram, if necessary. Choose Bending Moment item, to display the bending moment diagram. The scale of the diagram is adjusted, using the slider control. Choose Deformed Shape item, to display the deflection diagram. Multiple diagrams can be displayed simultaneously, by overlaying them. Press Shift key, and choose Shear Force and Bending Moment items consecutively. Now, the shear force, bending moment and deflection diagrams are displayed together in an overlaid image. Choose Separate Diagram item to separate the diagrams into 3 separate diagrams. In addition, there appears the applied force diagram, with representation of applied forces on the model image. Move the view of the diagrams by dragging with right mouse button pressed, so that all the diagrams may come within the visible window frame. Each of the diagrams can be dragged independently to desired positions. Draw the diagrams apart further, by dragging one by one. Now, we will observe the relationship between the diagrams. If you place the screen cursor at a point on the shear force diagram, a yellow tick box shows the information about the shear force at the position. At the same time, the shear force direction is indicated by a rectangular segment with two arrows, shown over the model image. If you place the screen cursor at a point on the bending moment diagram, a yellow tick box shows the information about the bending moment at the position. At the same time, the bending direction is indicated by a couple of arcs with arrows, drawn on the model image. If you place the screen cursor at a point on the deflection diagram, a yellow tick box shows the information about the deflection at the position. If you move the applied point force, all the diagrams are redrawn simultaneously, reflecting the movement of the force. Likewise, modifying any attributes of the model causes instant redrawing of the diagrams. If you click a point on the shear force diagram, there appears a green line, connecting the applied force diagram and shear force diagram. It is indicated in the two diagrams that the magnitude of shear force at the point is equivalent to the summation of the forces in the left side of the green line. The summation includes nodal reactions, distributed forces and point forces. At the same time, the line tangent to the bending moment diagram is drawn, and it shows that the slope of the tangent line is equivalent to the shear force. If you drag the green line, the value of the shear force changes, and the indication of the relationship is updated instantly following the green line. The slope of the bending moment diagram is also updated. If you click another point on the shear force diagram, there appears a new green line. Now, there are two green lines. This drawing implies that the variation of the shear forces between the two green lines is equivalent to the summation of the forces between the two green lines. This represents the mathematical relationship between the external forces and shear forces. As you move any one of the two green lines, then the representation of the relationship is also updated instantly, following the movement of the green line. It is also indicated that the difference between the slopes of bending moment diagrams at the 2 points is equivalent to difference of the shear force. This implies the mathematical relationship between the shear force and bending moment. If you click a point of the bending moment diagram, there appears a green line, connecting the shear force diagram and bending moment diagram. It is indicated in the two diagrams that the bending moment at the point is equivalent to the highlighted area of the shear force on left side of the green line. In addition, the line tangent to the deflection diagram is drawn. If you drag the green line, the value of the bending moment changes, and the indication of the relationship is updated instantly, following the green line. If you click another point on the bending moment diagram, there appears a new green line. It is indicated in the diagrams that the difference of the bending moment between the two green lines is equivalent to the highlighted area of the shear force diagram. This implicates the mathematical relationship between the shear force and the bending moment. As you move any one of the two green lines, the representation of the relationship is also updated instantly, following the movement of the green line. The mathematical relationship between bending moment and deflection can also be observed, using deflection diagram. If you click a point of the deflection diagram, there appears a green line, connecting the bending moment and deflection diagrams. The area of the bending moment diagram, on the left part of the green line, is highlighted in blue color. The slope angle of the deflection curve is proportional to the highlighted area of the bending moment diagram. The angle is represented in radian. If you drag the green line, the slope angle of the deflection curve changes, and the highlighted area is updated instantly, following the green line. You may select a portion of the beam by clicking 2 points on the deflection diagram. The boundary of the selected portion is represented by 2 green lines. The area of the bending moment diagram in the selected part is highlighted in blue color. As you move any one of the 2 green lines, the representation of the relationship is also updated instantly, following the movement of the green line. The difference between the slope angles at the boundary is determined by the highlighted area of the bending moment diagram. The mathematical relationship between the bending moment and deflection can be observed using this function. Going back to the relationship between shear force and bending moment, the bending moment reaches local maximum, or minimum value, at the points of zero shear force. In order to observe this relationship, select the shear force diagram and bending moment diagram at the same time by rubber band selection. Then, there appear green lines connecting the 2 diagrams. The green lines connect the zero crossing points in the shear force diagram, and the corresponding points in the bending moment diagram. These are the points where the first derivative of bending moment as well as the shear force falls to zero, and accordingly the bending moment reaches the local maximum, or minimum. If you move the applied point force, all the diagrams are changed simultaneously, and the green lines are moved in accordance. However, the green lines always pass through points of zero shear force and points of maximum bending moment. The next observation is the relationship between the zero bending moment and the deflection curve. In order to observe this relationship, select the bending moment diagram and deflection diagram at the same time by rubber band selection. Then, there appear green lines connecting the 2 diagrams. The green lines connect the points of zero bending moment in the bending moment diagram, and the inflection points of the deflection curve. Again, while moving the applied point force, the diagrams and the positions of the green lines are updated instantly. The green lines always pass through points of zero bending moment and inflection points of the deflection curve. These are the points where the second derivative of the deflection vanishes, as expressed by the relationship between the bending moment and deflection. No units are indicated for the numerical values shown in the diagrams, because the dimensional units are not designated. You may specify the units in the project setup. Choose Project Setup item of File menu. Then, Project Setup dialog pops up. Click Change Unit button in the dialog. Units Setting dialog pops up. Uncheck No Units box. Then, the radio buttons are activated for the units of force, length, time and temperature. Let's use the default setting, that is, kilonewton for force unit and meter for length unit. Click OK button to close Units Setting dialog. Newly designated units are displayed in Project Setup dialog. Close the dialog by clicking OK button. Now, corresponding units are indicated in the diagrams. This is the end of the demo for educational function illustrating the mathematical relationships between shear, bending moment and deflection diagrams of a structural beam.